Consider you have a rotating body. Okay, see, we have different masses at different points. Let's say m1, m2, m3 are different points which has different masses, and each of them they're rotating in different axes. So we have r1, r2, r3 to be the perpendicular distance from the axis of rotation, and all of them are moving with a different velocities, right? So we have v1, v2, v3, so on and so forth. So as we have v is equal to r omega, we'll get v1 is equal to r1 into omega, and v2 is equal to r2 omega, r3 omega, like this it keeps on going, right? Now see, the kinetic energy of the particle, that's basically kinetic energy is what? Half mv square. So here for each particle we have to calculate, correct? Let's say for particle p1 we have half m1 v1 square, right? Or in other words, in place of v1 we substitute r1 omega. So we have half m1 into r1 omega whole square, which gives us half m1 r1 square omega square. Clear? Similarly for p2 it will be half m2 r2 square omega square, correct? Right? So using this we'll get the kinetic energy of all n particles. So what is the total rotational kinetic energy? So we have to add the kinetic energy of all these particles, correct? So we will have k rotational is equal to half m1 r1 square omega square plus half m2 r2 square omega square plus so on and so forth. Omega square if you take common, so and half also you can take common. So we'll get half into m1 r1 square plus m2 r2 square plus m3 r3 square, so on and so forth, into omega square. You can write this as half sigma mr square omega square. What is what is sigma mr square? I, correct? The moment of inertia. So we get k rotational is equal to half I omega square. Okay, so this is the kinetic energy of a rotational body. Now, don't you think this is very similar to half mv square? Correct. So for a traditional translation motion of particle, the kinetic energy was half mv square, and the same thing goes with rotational body also, which is half I omega square. Okay. Now using this we can also define the moment of inertia. So if you transpose, see, we will get I is equal to 2 times of k rotational divided by omega square, correct? So if omega value becomes 1, then I will be 2 times of k rotational, correct? Or the kinetic energy of the rotational body, right? So what we can say is, if the angular velocity is 1 radian per second, then the moment of inertia is 2 times the kinetic energy of the entire body. Okay, when I say kinetic energy, the rotational kinetic energy, what we are talking about. Okay, so using this also we can define the moment of inertia. Alright, so kinetic energy was given by k rotational is equal to half I omega square, right? So see, now we have kinetic energy even for rotational body, we have moment of inertia, we have angular momentum, lot of these things, correct? Now again we have to figure out the relation between this kinetic energy and the angular momentum, because these two are also like very well connected. Just like how we have connection between each and every formula what we have studied for translational motion, the same thing is there even for rotational motion.